Welcome all. I'm very excited to be here. My first ACI. Today I'm going to talk about carbon-7 supercapacitors, a disruptive technology for renewable energy storage. I'm a research scientist at MIT, CS Hub, and I also would like to acknowledge my supervisor, Professor Franz Ullmann, Professor Admir Masic, as well as collaborators, Professor Yaksha Horn, James Weaver, and Nico Chanu. We all know about how concrete performs. High performance relative to its low cost. So it's very hard to replace this material with alternative, especially in the volumes that we require this material for infrastructure. Nevertheless, the impact of this material on the environment is also quite significant, and therefore this cost effectiveness might change due to carbon tax in the future. So we need to address this environmental impact of concrete. Second challenge that we are facing currently is energy storage challenge. When we want to transition from fossil fuel energies to renewables, we need a high bulk energy storage quantities. And the reason is behind it that we cannot simply control nature. Whenever we need, there is mismatch between supply and demand of energy. When we need more energy from fossil fuels, we just simply burn more. But when it comes to nature, we have to take it when nature gives us, and then store it and use it whenever we need it later on. So to tackle these two problems, the question is, can we tackle these two? And to kill two birds with one stone, we use literally artificial made stone concrete, which we alter by addition of nanocarbon black particles to make it electron conductive carbon concrete, which I'm going to call EC cube. This material not only serves as load bearing capacity, but also delivers other functionalities, high impact functionalities. Freeze-store resistance due to hydrophobic nature of nanocarbon particles, self-heating due to Joule effect. These two functionalities were very well explained and explored by Professor Pelonk on Sunday's session. This material can also serve as shielding against high-power electromagnetic impulses due to Faraday cage effect. But today I'm going to focus on the energy storage. So we want to use this material, EC-cube material, as a structural supercapacitor. So then we can imagine if we have an off-grid house powered by solar panels. As I mentioned before, we need batteries to store energy and use energy when needed. So our solution is to use EC cube as existing structural components, foundation, columns, and so on, and get rid or reduce the amount of batteries. So that's how we can see how it impacts the environment. It's not reducing CO2 when producing this material, but it's indirect CO2 emission due to reduction or elimination of batteries. How to make EC cube? We just use dry mix, adding nanocarbon particles, which are hydrophobic. So proper dispersion is the key. It clumps with addition of water, but at the same time, we don't want to disperse it to create separate islands. And the technology has already been developed, and I cannot take credit out of it, from it. Functionalities were presented in the patent 2020, Pelonk et al. Heat conductivity energy storage. There was optimization of nanocarbon type superplasticizer paper in 2020. But what I want to talk today about is scalability of this material. Because if we cannot transition our invention from the small scale laboratory to industrial application, then all is in vain. Before I move forward to the scalability of this material, we explored at first how nanocarbon particles form and that conductive network in our material. So we used the correlative EDS and Raman spectroscopy techniques, and then EDS gave us easy access to differentiate nanocarbon particles characterized by specific Raman spectra with D and G bands, and then differentiate it from other clinker phases or hydration products. That was very important because we wanted to distinguish nanocarbon particles from carbonated products, which both contain carbon. So EDS spectroscopy is not simply enough to give us this input. So here I'm presenting EDS map of carbon content, which is separated already from that non-carbonated natural carbonated product, and we can see how it shows space filling volumetric wire inside. Then further analysis, using further analysis, we could distinguish between low and high density, or more precisely low and high concentration nanocarbon network, which is basically phase of nanocarbon particles intermixed with hydration products, CSH, Portlandite, and so on. What is also remarkable that this volumetric space filling volumetric wire is present at different length scales, showing us that fractal dimension. Analysis of these two phases, low density and high density concentration phases, we employed statistical descriptors, namely two-point probability correlation function. We obtained mean chord length, which can be seen linearly scales with the concentration of other nanocarbon particles. So this is indicative of unique specific texture of these phases, and at the same time shows us that no matter what type of nanocarbon black we use, the concentration, then the whole process and volumetric wire this process is repetitive, highly repetitive, and reproducible at different configurations. Currently, we are also investigating it in 3D using FIB-SEM techniques to also reduce the resolution further. So now let me move to when we see that this material can be used as electron conductive material. Now the question is how we can employ it and use it as energy storage. So we use it as energy storage as a supercapacitors. So when supercapacitors function is the same as battery to store energy, but how they work is completely different. Batteries work based on chemical processes, while supercapacitors work on double layer effect. Three main components of supercapacitor: electrodes separated by a separator, and all soaked in electrolyte. So electrolyte is that medium that carries ions. And in this assembly, carbon cement composite is that playing a role of electrode, while hydration porosity serves for transport. And then here's the CT image from Soleil Synchrotron Paris, which can show that more than 90% of hydration porosity is interconnected. So that gives us that possibility that ions can reach to nanocarbon particles. So here we can see that our EC cube material, two electrodes are separated by a glassy fiber separator, and all is soaked in electrolyte. Exemplary can be KCl solution of different concentrations. When we want to quantify how much of energy, because this is the key point, to quantify how much of energy we can actually store, we perform galvanostatic charge-discharge tests, cyclic voltammetry tests. Here I'm presenting just CV curves, where we applied constant rate of voltage and we monitor current. While charging and discharging, we have those loops, hysteresis, and area under these curves gives us information how much energy we can store. Then we perform these tests at different scan rates, and we can reach to rate-independent capacitance. This is important since we want to obtain the values which are invariant with laboratory conditions. Further, we are showing that rate-independent capacitance can be scaled with dimensional diffusion variable. So we can see that all experimental results for different water-to-cement ratio, different nanocarbon black characterized by different specific surface, and also what is extremely important here, different thicknesses, different size of the sample, because this is diffusion-driven process. You can see that they all align with the mathematical model error function, and then based on this we can make an estimate that it can store roughly between 20 to 220 watt-hour per meter cube. And I can tell you right away that this value is extremely low when we compare to regular supercapacitors. Nevertheless, we need to keep in mind how much of concrete we are using in our structures. Then these numbers can play significant role, because 45 meter cube of this material can be enough for average need of residential house. That's a very important message. In the whole story, I talk a lot about electrode, but I mentioned that supercapacitor is also composed of electrolyte because all is soaked in electrolyte. And there are many different types of electrolyte that could be used, but we have to identify the one with specific properties. High diffusion coefficient, high ionic conductivity, negligible effect on our material, and relatively low cost. The last factor is these last two factors are the most important since we want to use it as a bulk supercapacitor, so we're going to use a lot of electrolyte. And I totally agree with Nano Energy paper where they mentioned that no perfect electrolyte has yet been developed, especially for this unique application which we are presenting now. There are multiple options: aqueous, organic solvents, ionic liquid, gel-like forms, and so on. Based on these four properties, we selected few of them: potassium chloride solution, also the one based on propylene carbonate, and gel form or KCl solution. And some feedback from our tests, we can see that not only choosing the type of electrolyte, but also its concentration, we affect the properties. We affect the capacitance of our system. Here, KCl solution, different concentration from 0.5 to 3 molar ratio and the capacitance, and we can see that there is some kind of optimization that can be performed at different length rates, scan rates, keeping in mind that higher molarity ratio and results in higher ionic conductivity, but at the same time lower diffusion coefficient. Then when we compare, let's say, aqueous and organic solvents, we can see that, as I mentioned before, the area is indicative of the energy, how much we can store. We can see that aqueous solution, the black hysteresis here, from 0 to 1 volt can store slightly more energy than organic solvent, and this is because of diffusion coefficient. Nevertheless, we cannot exceed more than 1.23 volt for water not to deal with splitting of water into hydrogen and oxygen. So with organic solvents, we can reach to higher voltage windows. So that gives us advantage. So first we use organic solvent. So we just had to use one supercapacitor cell and get more than 2 volts. And we were able to light LED. That was a very important date to me. 5th of May, Cinco de Mayo this year. Very exciting experience, I have to say. Later on, we move also to KCl solution. As I mentioned, we need to reduce cost of this electrolyte. It's very important. So to overcome the issue of that barrier of 1 volt, we have to connect our supercapacitors in series to increase that voltage window. And here, using photovoltaic cells, we were able to charge our supercapacitor cells and then use it later on to deliver power and light LED. Further scaling is also possible. Recent prototype 12-volt supercapacitor, we can see that we can reach to 12 volts. This is our Oreo design of supercapacitors connected in series. Now we are also working not only on increasing the voltage window, but also how much of energy we can store. So further scaling of the size of the material. What is also very important, we were able recently to scale it up from cement paste to mortar scale. This is extremely important, especially when we talk about a load bearing capacity, right? So of course there is dilution effect in this case, but this technology still is viable. When we talk also about supercapacitors, battery technology, there are different aspects that we have to keep in mind. For example, how the retention of the capacitance goes with number of cycles of charge discharge. So we were able to reach to more than 10,000 cycles without losing a lot of the capacitance. Usually that drop was associated with drying of not properly sealed samples, so that was not the other issue. Also, how hydration time can affect the capacitance. Test performed after 1 month and 30 months showed comparable capacitance, which is also extremely important. And then I'm showing the percolation threshold, which is needed to obtain that capacitance and energy storage functionality. It's slightly higher than when it comes to just conductive functionality, but still it's low. So here I hope that I showed and deliver the message that this DC cube technology exhibits promising scalability, spanning from 1 volt to 12 volts and so on, from cement paste to mortar. And then it shows range potential applications and brings us closer to the most important goal, which is transition from fossil fuel-based economy to renewables. So now, as Professor Ulm says, engineering starts now. So now it's all about optimization, further scalability, smart design, that all can lead us to further future large-scale applications. Off-grid houses, energy buffer for renewables, and then high-end applications, smart charging roads, which is more tricky since we have to switch from DC to AC technology and high frequencies. Nevertheless, it's also the option that we are exploring. Thank you so much for your attention. If I couldn't answer all questions, please reach us at my TCS Hub or my email. And I would like to acknowledge my TCS Hub and so. Thank you so much.
We still have time maybe for a few questions. It's perfect timing. We had like one presentation meeting, but we spread over. I think that it was excellent in terms of timing, but we have time for maybe one or two. Yeah, please approach the microphone and introduce yourself.
Hello, thank you very much. Gianni Muciaccia, Preco di Milano, Italy. Thanks for sharing. I have a few questions I will try to put on the table. First one, as alternative to the traditional battery cell, we know that one of the issues with traditional cells is the fact that we don't have enough raw material worldwide, okay? If we have it concentrated in some parts. So if we go to real scaling up here, how much do we need of that? I mean, do we really have the resources to build high quantities of concrete in this way? So, I mean, it's a question if you are facing that. Second one is, if I study correctly, well, you will need an electrolyte, any way to process, to push. And then to some extent, we might say or not, you will tell me that we also need water in the concrete. So my question was, when time goes by and water starts to, evaporate, let's put it like that, can this decrease, the capacity here through time? And third of all, very silly, if I put two hands on the wall, do I get struck by lightning because of voltage or not? Thank you very much.
Thank you for your questions. The first question is very important, and I should have shown it and mentioned it in the presentation. Yeah, that's the first question regarding do we have enough material? And that's what we use advantage of this material, because all the basically ingredients are abundant worldwide. For batteries, there are limited resources. With this technology, we use a huge amount of cement, concrete, and so on. And nanocarbon black is also present everywhere. So that's a huge advantage of this technology, that we can really have huge quantities. Second one about electrolyte. Yeah, electrolyte is extremely important because we need that transport of ions and reach to all nanocarbon particles. So our system would have to be sealed. So we can imagine when it's all about design right now. So this will not be regularly used, let's say, column. Let's imagine that Oreo design as a core of the column, and outside would have to be, for example, impermeable concrete and so on. Or we also aim at the applications where the surface is not exposed too much to the environment, for example, as properly sealed pile foundation and foundation and so on. But this will be a challenge while designing these structures. And the third one, fortunately, we are dealing here with low voltages and low. Yes. So the last one should not be the issue.
Maybe you can charge your telephone. Yes, one more question, please.
Hi, very interesting work. In one of the slides, I saw upwards of 10% of weight nanocarbon. Mm-hmm. I think I'm not an expert, but I think you lose a lot of mechanical properties with that, right? Is there a way to enhance the conductivity while reducing the nanocarbon? So, like, you sacrifice less mechanical properties while maintaining the conductivity.
Yes, that's the extremely important question, especially when we are talking about concrete, when load-bearing capacity is the main function. And with these quantities of addition of nanocarbon black, we reduce mechanical performance drastically. There is another part of research we are trying to run to restore that lost mechanical performance, application of different type of cements and so on. So that we'll have to restore. But there is always a sweet spot, how much of energy we can get and not losing too much of energy. But this is the whole investigation that we will have to run. How we can also improve the capacitance. We showed maybe not in the presentation, but in the recent PNAS paper, that the energy storage scales linearly with the specific surface of nanocarbon black. So we can use, let's say, nanocarbon black has higher specific surface at the same volume, and that can also help. But there will be a lot of work that we'll have to perform. But still, the whole benefit that we get out of it, it's much more important than losing, and especially in applications where we don't need that much of strength for foundation and so on, this can be overcome. Thank you.